So students, this is lecture number 2 on limits. In lecture number 1, we have discussed about epsilon delta definition on limits and some theorems related to it. Okay. So now in this lecture, we will discuss some more theorems and examples related to the definition. So article 4, if limit x goes to a, fx equal to 0 and g is bounded in a deleted neighborhood of a, then limit x goes to a, fx into gx equal to 0. So g is bounded in a deleted neighborhood of a and limit x goes to a, fx equal to 0. Then if we take the limit of the product of fx and gx, then at x goes to a, then x tends to a, fx into gx goes to 0. Article 5, limit x goes to a, fx exists finitely, then for any epsilon greater than 0, there exists delta greater than 0 such that mod fx1 minus fx2 less than epsilon for 0 less than mod x1 minus a less than delta and 0 less than mod x2 minus a less than delta. So if we take any two point in the neighborhood of a minus delta and a plus delta, if I take x1 here and x2 here, and the distance between x1 and x2 is less than delta, this is my delta. So what happens if we take any 2 point in the interval x1 and x2, the function f of x1 minus f of x2, also the estimation of fx1 and fx2 also less than epsilon. If this happens, then we can say the limit of the function exists finite. If it doesn't happen, then limit does not exist. So we also solve some examples related to article number 5. Okay, so let us start some examples related to epsilon delta definition. So before that, we quickly revise what is epsilon delta definition. A function fx has a limit L as x tends to a, that is limit x goes to a, f of x is equal to L, if and only if given epsilon greater than 0, however small, there exists a delta greater than 0. This delta depends upon epsilon. So we write this delta depends upon epsilon such that mod fx minus L is less than epsilon for 0 less than mod x minus a less than delta. So this is epsilon delta definition on limit. So let us discuss one example. Using definition of limit prove that limit x goes to 2, 4x minus 5 is equal to 3. Limit x goes to 3, 1 minus 3x is equal to minus 8. Limit x goes to 2, 4x minus 5 is equal to 3. Limit x goes to 1, x square minus 1 upon x minus 1 is equal to 2. Limit x goes to 2, x square minus 4 upon x minus 2 equal to 4. Limit x goes to 3, x square minus 9 upon x minus 3 equal to 6. limit x goes to -1, 2x plus 3 equal to 1, limit x goes to 3, 11 minus 2x equal to 5, limit x goes to 3, 1 minus 3x, even 2 minus 3x, x goes to 2, 2 minus 3x is equal to -4. So let us discuss these examples. So first part, limit x goes to 2, 4x minus 5 equal to 3. So if we compare this with limit x goes to a, f of x is equal to L. So here what we get? Here f of x is equal to 4x minus 5 and L is equal to 3, and point A is point A is 2. So we have to keep the definition, epsilon delta definition in our mind this. So given epsilon greater than 0, if we take any epsilon, however small, positive epsilon, however small, we find a number, a positive real number, delta, that delta depend upon epsilon, so that the estimation of fx and the point L, the limit, is less than epsilon for mod x minus a, that is less than delta, because we are not considering the point. So mod x minus a is greater than 0. So we have to first estimate mod fx minus l. We start with this. First we find what is the estimation of mod fx and l. So mod fx minus l, that is equal to mod 4x minus 5. This is fx minus 3, and that is equal to mod 4x minus 8. And if we take 4 common, so we get mod 4 into x minus 2, and that is equal to mod 4 into mod x minus 2, because mod AB equal to mod A into mod B. For all, any, you can take any real number A, B, that mod A, B, A into B, that is mod A into mod. And mod of 4 is 4, mod x minus 2. So we get this. Now we estimate mod fx minus l, and we get 4 into mod x minus 2. So now we use epsilon delta definition. So given any epsilon greater than 0, however small, we can also fix this epsilon. Right? So if we take any epsilon greater than 0, however small, there exists delta, positive real number delta, such that this delta depend upon epsilon. So we have to find this delta, right? Such that mod fx minus L, this must be less than epsilon. And what is mod fx minus L? This implies 4 into mod x minus 2. So we can write here, this implies 4 into mod x minus 2, that is less than epsilon. Now we have to estimate mod x minus a. Here a is 2, so we have to estimate mod x minus 2. We have to find out this, right? So mod x minus 2 means Now we, we have 4 into mod x minus 2. This is less than epsilon. So what we do? We take, we multiply both sides by 1 by 4. So if we, because 1 by 4 is a positive number, real number. So if we multiply it with a positive real number, then there is no change in the inequality. Right? So if there is minus 4, if there is minus 4, then if you multiply it by negative sign, then inequality change. But because it is 4, so if we multiply both sides by 1 by 4, then we get this 4 and 4 cancel out. So this implies, because 4, 1 by 4 is the multiplicative inverse of 4. So we can write the product of this 1 upon 4 into 4, that is 1. So mod x minus 2 is less than epsilon by 4. So now our objective is to, we have to find mod x minus a is less than delta. Right? So we find out, if we take this to be delta, then we say delta is equal to epsilon by 4, then by definition of limit, mod fx minus L is less than epsilon for mod x minus 2 less than delta, where delta is equal to epsilon by 4. If we choose delta equal to epsilon by 4, so this implies that by definition of limit, we can also write this as limit x goes to 2, f of x is equal to L. This implies limit x goes to 2. What is fx? Fx is 4x minus 5. 4x minus 5. This is equal to 3. Now, here you can find delta to be epsilon by 4. It means this delta depend upon epsilon. If we take epsilon equal to 1 by 2, then what is delta? Delta is 1 upon it. If we take epsilon to be 1 upon 4, then this delta is 1 upon 16. So when epsilon change, delta change. It means delta depend upon epsilon. Right? That's why we said that in the definition, this delta depend upon epsilon. It may be equal. It may be double of epsilon. It may be half of epsilon. It may be 1/4 of epsilon. That we have to find it. This is just for thinking. Right? Let us discuss one more example related to the same article. Let us discuss seventh part. Limit x goes to -1, 2x plus 3 equal to 1. This is seventh part. Limit x goes to -1, 2x plus 3 equal to 1. So here fx equal to, here fx is equal to 2x plus 3. Limit L is equal to 1. Point A is equal to -1. So we have to estimate fx and L. And we have to find mod x minus a. X minus a means mod x minus -1. That is mod x plus 1. We have to find mod x plus 1. Right? Okay. So let us estimate first. Given epsilon greater than 0, given any epsilon greater than 0, however small, there exists delta greater than 0, delta depends upon epsilon, such that mod of fx minus L. So we first estimate this. So fx minus L, that is equal to, or we can write the definition, that is less than epsilon for 0 less than mod x plus 1 less than delta. So we have to find this delta. We fix epsilon, or we can take any epsilon, positive. So according to that epsilon, positive epsilon, we have to find it. So we estimate fx minus l. What is fx? This is 2x plus 3. And what is l? This is 1. So this is equal to mod 2x plus 2. And we can take 2 to be common. This is x plus 1. And that is equal to, again we can take mod a into b, that is mod a into mod b. And mod of 2 is 2. So we get mod 2 mod x plus 1. Right? Now we use the definition. Now mod of fx minus l, this is less than epsilon. This implies or we can say this is equal to 2 times mod x plus 1, right? This is equal to this, and this is less than epsilon. This is less because mod fx minus l is less than epsilon. So we have estimate mod fx minus l, that is equal to 2 into mod x plus 1, and this is less than epsilon. What is the meaning of this? This implies mod x plus 1 is less than epsilon by 2. How we find this to be less than epsilon by 2? We multiply both sides by 1 by 2. It is a positive number. So by multiplying 1 by 2, there is no change in the inequality. So mod x plus 1 is less than. So this is our delta. If we choose delta to be, choose delta is equal to epsilon by 2. So we find out that this implies that mod fx minus l is less than epsilon for 0 less than mod x plus 1 less than delta, where delta is equal to epsilon by 2. So delta depend upon epsilon. If we take epsilon equal to 1 upon 10, or if we take epsilon to be 1, then delta equal to 1 upon 2. If we take delta epsilon equal to 1 upon 10, delta equal to 1 upon 20. So when delta epsilon change, delta change. So delta depend upon epsilon. So what is the meaning of this? This means that x goes to minus 1, f of x is equal to L. And what is fx? So limit x goes to minus 1, 2x plus 3 is equal to 1. Go through these two examples, PRP, pause, review, and proceed. Pause, review, and proceed. So take a pause of 2 to 3 minutes and then revise the part. If you have any difficulty, go through the previous video lecture and then try to use the definition. Now, I hope you can solve question number 3, 2, 3, 8, as well as 9. So try these questions. Question number 2, 3, 8, and 9. Now let us discuss question number 4 or question number 5. We start with question number 5. 4, 5, and 6, they are same. Limit x goes to 2, x square minus 4 upon x minus 2, that is equal to 4. So here fx equal to x square minus 4 upon x minus 2, limit L equal to 4 and point A equal to 2. So given, what we do, we take given epsilon greater than 0, however small, there exists delta greater than 0 this delta depend upon epsilon, such that mod fx minus L is less than epsilon, or mod x minus A less than delta, right? So what we do, we estimate mod fx minus L. But mod fx minus L is x square minus 4 upon x minus 2, and L is 4. So we can write x square minus 4 as x minus 2 into x plus 2, x minus 2 minus 4. This is cancelled. So we get mod x plus 2 minus 4, and that is equal to mod x minus 2. So we estimate mod fx minus L, and we get this is mod x minus 2. Now because limit of the function x goes to 2, so we have to find out mod x minus 2. So we get, now by using definition, mod of fx minus L, that is equal to mod x minus 2, we get this, and our we have to estimate that, we have to find out that mod of fx minus L is less than epsilon. Now can you tell me what is that, what is delta here? So mod x minus 2 less than epsilon, it means, this implies that mod x minus 2 less than epsilon, it means I can choose the same delta, same epsilon to be my delta, right? So therefore mod fx minus L is less than epsilon for 0 less than mod x minus 2 less than delta. Here delta is equal to epsilon. If I take epsilon to be 1 by 2, then my same delta will work. Whatever epsilon I choose, positive real number, epsilon I choose, the same delta will work. Okay? So this implies that limit x goes to 2, f of x is equal to L, and this implies limit x goes to 2, x square minus 4 upon x minus 2, that is equal to 4. So take a pause of 30 seconds and revise this part quickly. So you can try these question number 6 and question number 4. Also you can try this one. Even we have already completed. So all the 9 parts are completed. So you can try all the remaining parts. Okay, so now let us come to another problem. If we have let f of x is equal to 2 plus x if x is rational, and 2.5 minus x if x is irrational. So I can, instead of writing x is rational and irrational, I can write x belongs to Q, which means x is rational, and x belongs to Q complement or r minus Q, that is irrational. R minus Q means x is irrational, or we can also write Q complement, that is irrational. So prove that limit x goes to 0.25, f of x is equal to 2.25. This is first part. Second part is f of x is equal to 5 plus x if x belongs to rational, and 5.5 minus x if x belongs to irrational. So prove that, what we have to prove that limit x goes to 0.25, f of x is equal to 5.25. So discuss, let us find the solution of first part. So given f of x is equal to 2 plus x, 2.5 minus x, if x belongs to rational, if x belongs to irrational, that is r minus q. So we have to estimate fx and l. So what is fx here? Fx is 2 plus x for rational and 2.5 minus x for irrational. What is the limit? This is 5.25. This is the limit. What is the point? 0.25. So we have to keep these limit and point in our mind. So now what we do, we have to estimate if x is rational. So we divide this question into two parts. First part, first part, if x is rational. Rational means that is x belongs to q. Now we have to estimate fx and l, mod fx minus l. That is equal to, what is fx? If x is rational, then fx is 2 plus x. So this is my fx because x belongs to q. So I can write 2 plus x minus l. What is l? This is 5.25. And this is equal to x minus 2.5.25 minus 2 minus 5.25, that is equal to 3.25. Oh, actually, this is not the limit. This L is in 2.25. They are considering the limit of second function. This is not the. Okay. So this is our function. This is fx, and this is the limit 2.25, and this is the point x equal to 0. X goes to 0.2. So we take L to be 2.25, not 5.2. So it is 2.25, and when we take the difference, it is minus 0.25. So when we estimate fx, mod fx minus L for x belongs to rational, then we get mod x minus 0.25. So second part, second case, even instead of second part, we consider case, first case and second case. Case 1, case 2. Case 2. If x is irrational, if x is irrational means that is x belongs to r minus q. So what is mod fx minus l? That is mod 2.5 minus l. X, fx is equal to 2.5 minus x because x belongs to r minus q. Minus the limit remains same, 2.25. We get 0.25 minus x, and we can also write this as minus of x minus 0.25, and we get this to be mod x minus 0.25. So in both the cases, what we get, fx minus L is same. If we take rational, then again we estimate fx minus L, we get mod x minus 0.25. If we take x to be irrational, then again we get mod fx minus L to be x minus 0.25. So in both the cases, it means in general we can write mod of fx minus L is equal to x minus 0.25 for all x belongs to R, because it is, if it is true for rational as well as irrational, it means it is true for every real number. Now we can use the definition. So therefore, given epsilon greater than 0, let epsilon greater than 0, however small, there exists a positive real number delta. This delta depend upon epsilon such that mod fx minus L, that is equal to mod x minus 0.25. So this is less than epsilon, because we have to estimate mod fx minus L to be less than epsilon. It means we get mod x minus 0.25, this is less than epsilon. So what we take, we take delta to be my epsilon, right? So let it be delta. So we can say this implies mod fx minus L is less than epsilon, or mod x minus 0.25 less than delta. Here my delta is same epsilon. So this implies that limit x goes to 0.25, f of x is equal to 1. Then put the value of fx and then we get the answer. Okay. On the same way, you can try the second part, this one. Okay. So now let us move further and now we'll discuss some examples related to article number 5. This is example number 3. Prove that limit x goes to a 1 upon x minus a does not exist. So here fx is equal to 1 upon x minus a. So what we use article number 4 to prove this. What we do, we take any 2 point x1, x2 in the in the neighborhood of point A. That means x1 and x2 lies in between a minus delta and a plus delta. Now we have to estimate that fx1 and fx2. If we take the estimation of fx1 and fx2, that must be less than epsilon. So we can take any epsilon. Epsilon is positive real number. Epsilon is greater than 0. But we can fix it is true for every epsilon. But here we see that if we take particular epsilon, then this result is not okay. So fx equal to 1 upon x minus. So let epsilon greater than 0, however small. Epsilon is positive, but however small. So we take epsilon to be greater than 0, but less than 1. We fix epsilon. Even we can not say that we fix epsilon, but we can take epsilon to be positive, but less than 1. You can take any epsilon less than 1. So let there exists according to this epsilon, we have to find a we find that there exists a number delta, positive real number delta. This delta depend upon epsilon. So delta greater than 0, we a positive real number. Now choose. Now what we have to do? We have to take a neighborhood at point A. Now we have to take x1 and x2. x1 and x2 in any point in between. If I take x1 here and x2 here, now we have to, according to this fx1 and fx2, x1 and x2, we have to find fx1 and fx2. So fx1 minus fx2 is mod of fx1 minus fx2 is less than epsilon. We have to find it. Is it true for every epsilon? If this is true for every epsilon greater than 0, then the result, then we can say limit of the function exists. But if it is not true, then we can say the limit of the function does not exist. So we choose a number because delta is greater than 0. We choose a positive integer and such that this 1 upon n is less than delta. So if I take delta here, delta is any positive real number. So I have to choose my 1 upon n. I have to take n positive integer n such that delta is greater than 1 upon n. If I take delta to be 1, then I can choose an integer n equal to 2. So 1 upon 2 is less than delta, less than 1. Even 1 upon 3, 1 upon 4, 1 upon 5, all are less than 1. So 1 upon n is less than delta. Now, since we know that for a positive integers, 2n is greater than n. 2n is greater than n. So if we take the reciprocal, then 1 upon 2n is less than 1 upon n. And by 1 upon n is less than delta. So we can find a relation. We can choose another integer 1 upon 2n in such a way that 1 upon 2n is less than 1 upon n, 1 upon n is less than delta. So 1 upon n is less than delta such that or we can say n is greater than 1 upon delta. So this implies since 2n is less than 2n is greater than n and n is greater than 1 upon delta, so we can take the reciprocal. So if we take the reciprocal, what happen? Because delta is a positive real number, so we can take the reciprocal. 1 upon 2n is less than 1 upon n is less than delta. So since my 1 upon n, 1 upon 2n, we find the relation between 1 upon n, 1 upon 2n and delta. And delta is greater than 1 upon n and 1 upon 2n. So if I take a here, my a plus 1 upon n, this, if I take 1 upon n here, so a plus 1 upon n, this is my a plus 1 upon n. And this is less than a plus delta. Because we know that a 1 upon 2n is less than 1 upon n is less than delta. If we add any real number, then a plus 1 upon 2n is less than a plus 1 upon n is less than a plus delta. So these number lies are less than a plus delta, and also these are greater than a minus delta. So if these two numbers are in between a minus delta and a plus delta. So I can draw another picture so that the concept may be clear. This is my a minus delta. This is a plus delta. So my 1 upon n lies here. So a plus 1 upon n, this is a plus 1 upon n, and this is a plus 1 upon 2n. Right? So I take this to be x1 and this point to be x2. So these are my 2 point x1 and x2. They lies in the interval of a minus delta and a plus delta, but they are not equal to a. The points are not equal. Right? So now let x is equal to, and my x1 is equal to a plus 1 upon n, and x2 is equal to a plus 1 upon 2n. These x1 and x2, x1 comma x2, they belongs to uh, you can say the two real numbers satisfying 0 less than mod x minus a less than delta. So they are any 2 point between this interval, between the deleted neighborhood of it. So then fx1, what is fx1? So fx is given, fx is 1 upon x minus a. So what is fx1? 1 upon x1 minus a. 1 upon x1 minus a. And now we have choose x1 to be a plus 1 upon n. So x1 is a plus 1 upon n minus a, that is equal to n. What is fx2? Similarly, we can find this is equal to 2n. Now mod fx1 minus fx2, that is equal to mod n minus 2n, that is equal to mod minus n, that is equal to n, and n is greater than equal to 1, and my epsilon is less than 1. I take epsilon is less than 1, but here it is 1, so which is greater than epsilon. So this implies that mod fx1 minus fx2 is greater than epsilon for 0 less than mod x1 minus a less than delta, and 0 less than mod x2 minus a less than delta. This we can say that if it is less than epsilon, then the limit exists, but if it is greater than epsilon, then we can say limit x goes to a 1 upon x minus a does not exist. Does not exist. Again, go through the proof. Even if you found any difficulty, try to think about this geometrically, and also uh, try to find out the relation between these inequalities. Right? It is not necessary that you can take 2n and n. You can take 3n, n by 2, 4 and 5 and 2n plus 1, 2n plus 2, right? So you can take any number. Even we can take 3n and n. 3n is also greater than n. So you can take any two number between the interval. So try these example. So this is an exercise to you. Limit x goes to 1 upon x minus 1 does not exist. This is the first part. Second, limit x goes to 0 sine 1 upon x does not exist. Limit x goes to c 1 upon x minus c does not exist. Okay. One more example. To evaluate limit x goes to 0 x into sine 1 upon x. So we have to evaluate the limit x goes to 0. So in some examples, we make the use of article number 5. In some examples, we make the use of article number 4. So in article number 4, what we get, if limit x goes to a fx equal to 0 and g is bounded in related neighborhood of a, then limit x goes to a fx gx equal to 0. So we try to use the result in this example. So let f of x here, f of x be x, and g of x will be sine of 1 upon x. So what is, we have to estimate, we have to evaluate the limit x goes to 0. When x tends to 0, x into sine 1 upon x. So limit x goes to 0, f of x. Limit x goes to 0, f of x is equal to x, that is 0. So f of x की limit x goes to 0 के ऊपर 0 आ रही है, तो first point is done. Limit x goes to a fx equal to 0. Now second thing, we have to check whether g is bounded in the deleted neighborhood of 0. So for boundedness, how we can check the uh, that function is bounded? The function is said to be bounded if there exists m greater than 0, m is any real number such that for all x belongs to domain, x belongs to D, domain of the function, right? Domain of the function such that mod of f of x is less than equal to m. So if mod of f of x is less than equal to m for any positive real number, then we can say the function is bounded. So here we have to check mod of gx, that is equal to mod sine 1 upon x. And this is, we know that sine function is, this is bounded function, but 1 upon x. So x at x is equal to 0, this is not defined. So what we do, because we have to find the function g to be bounded in a deleted neighborhood of, so we are not considering the point 0 here. 0 is not, we cannot take x equal to 0. So for all other value, the function exists, right? We can find the value of sine 1 upon x. So, and we know that this is a bounded function, so this is less than equal to 1 for all x belongs to the deleted neighborhood of 0. So therefore g is bounded. So we can say, given any x belongs to R, you can give me any such that mod of gx is less than equal to 1. This implies that gx is bounded. G is bounded, not you can say gx, g is bounded. G is bounded in deleted neighborhood of 0. So we can use the theorem. Now by theorem, if limit x goes to a, f of x equal to 0, and g be a bounded function in a deleted neighborhood of a, then limit x goes to a fx into gx equal to 0. So limit equal to 0. So we can use this theorem. So we can write limit x goes to 0 x into sine 1 upon x. Fx is x, gx is sine 1 upon x, that is equal to 0. Again, PRP, pause, review and proceed. Go through this, the proof of this, and try to solve some examples. Again, exercise, evaluate limit x goes to 1, x minus 1, sine 1 upon x minus 1. This is the first part. Second, limit x goes to 0, x square cos 1 upon x. Third, limit x goes to a, x minus a, sine 1 upon x minus a. Fourth, limit x goes to 0, x square into sine 1 upon x. And fifth, limit x goes to a, x minus a, cos 1 upon x minus a. So try these. Lots of exercises are given to you in this video lecture. Try to solve all these exercises, and we will discuss new theorems in our next video lecture. Thank you. Have a nice day.